Welcome back to the Math Professors. And what I want to do is I want to tackle an optimization problem. And I'm going to do this using a Calculus 1 approach. And then we'll take this to a Calculus 3 approach since we just introduced Lagrange multipliers. So you would have seen a problem like this in Calc 1. It says a 216-meter rectangular p-patch enclosed by a fence and is divided into two equal parts by another fence parallel to one of its sides. What are the dimensions of the outer rectangle that would require the smallest total fence? So let's start with an image of this. So what we have is we have this rectangular p-patch, and we know that the area is going to be 216. Moreover, we know that this thing is sliced into two. It says parallel to one of its sides, so we can go here. And it doesn't really matter. I have students ask, well, what if it went this way? Well, you'll still get the same dimensions. All right, so what I need to do is label these things. So since this is going to the x direction, let's call this side x. And since these things are going to go in the y direction, let's call these three sides y. So basically, this sets up a system of equations. What I know is I know the area of this thing, and I want to minimize its fence. So let's set up the two equations. So I have an area equation, and then I have a fence equation. So your area is going to be equal to, well, the outer area is going to be x times y. So this is x times y. And it's constrained to a value of 216. Now the fence, we'll just call it function f. This is going to be equal to the sum of all the sides. So it's x plus x and y plus y plus y. So this is going to be equal to 2x plus 3y. Now to calc class, we like say, I'm trying to optimize this fence. I'm trying to find the maximum or the minimum in this case. And minimums happen at critical points, so that basically means its derivative has to be equal to 0. So the problem with the Calc 1 class is this has two variables. This has x and y, and all we know how to do is take the derivative of just one variable. So what I'm going to do is I'm going to solve this equation for one of its variables, plug it into here, and then I can take its derivative because this would now be a function of just one variable. So let's solve it for y. So y is going to be equal to 216 divided by x, and then I'm going to substitute it into here. So f is going to be equal to 2x plus 3 times 216 over x. So f is going to be equal to 2x plus 648 all over x. All right. Now that this is a function of one variable, I can take its derivative, I can set it equal to 0, and then go ahead and find these critical points. So f prime equal to 0. Well, the derivative of 2x is 2. The derivative of this, since this is x to the negative 1, is going to be minus x to the minus 2. So this is going to be minus 648 over x squared, and we are going to set that equal to 0. All right, so solving for x. So to the other side, 2 is going to be equal to 648 over x squared. So then 2x squared is going to be equal to 648. Divided by 2 is going to give us 324. And then finally square rooting. I know we get plus or minus, but we're only looking for positive links here. So x is going to be equal to 18. Once you know x is 18, you can plug this back into here. So y is going to be equal to 216 over 18. So y is going to be equal to 12. So those are the outer dimensions. X is equal to 18 and y is equal to 12. Now, since we just covered Lagrange multipliers, what we can actually see is, notice that these two functions are really multidimensional. So what I have is, I have a function on a constraint. Again, how do you know what one's a constraint? Well, the constraint is the one that has that's set equal to a constant. So I'm going to write this in letters. So let's say f of x comma y is going to be equal to 2x plus 3y. And then my constraint we call g of x comma y is going to be equal to this x times y, which is equal to 216. Okay, so we know that max and mins happen when their gradients are parallel. So this is when, you know, the gradient of f is parallel to the gradient of g. So the gradient of f is going to be 3 derivative with respect to x, derivative with respect to y, and this is going to be lambda times the derivative with respect to x is y, the derivative with respect to y is x, and then we set their components equal. So 2 is going to be equal to lambda y, and then 3 is equal to lambda x. So now solve. I'm just going to solve both of these for lambda and then set them equal to each other, because again our goal is to use the constraint to find the other variable, so the value of the variables. So 2 over y is equal to lambda, and 3 over x is equal to lambda. So that means they're equal to each other. So 2 over y is equal to 3 over x. So cross multiplying, 2x is equal to 3y, which means 2/3 x is equal to y. Now I can plug it back into the constraint. So plugging this in, we have x times y, which is 2/3 x, is equal to 216. So then I'm going to have 2/3 x squared, which is equal to 216. So 2x squared is equal to 648. And what we're noticing here is we have the same thing over here, don't we? So then x squared is going to be equal to 324. Which means x is equal to 18, and if x is equal to 18, y is going to be equal to 12. So let's kind of get a gist of this. So when we do optimization problems, what I tell people or tell students is that optimization problems really is kind of a system of equations with derivatives. So what we have is we have two equations. It's a system of equations because I have to solve one of them for a variable and substitute. So there's your system of equations with the derivative. Very similar. So what you do is you do the system of equations first, you do the derivative second, and with Lagrange multipliers, it kind of goes slightly the other way. You do the derivative first and the system of equations second, and you would get the same answers in both cases. So again, please consider liking, subscribing, and sharing. Thank you.